All right, yeah, good afternoon. I'm Walter Metzner, very grateful to the organizers of this conference for inviting me here. It's a very nice place. And yeah, I would like to tell you about a very rather recent story, a gauge theory of the pseudogap phase in CUPRATE superconductors. This is joint work with Pietro Bonetti, one out of several really outstanding Italian PhD students I have had in Stuttgart, and he has just finished his thesis and will continue as a postdoc probably in the US. Yeah, and okay, he was basically the most important person in this project. So there are also two other collaborators involved a bit previously in pre-stages of this, namely Demetrio Vilardi. He has been another of these Italian PhD students. He's now permanently in Stuttgart. Yeah, and here, last one, Johannes Mitscherling, German PhD student. He just moved to Berkeley to work with Joel Moore. Okay, so here's an outline. Maybe I do it faster, so not wasting too much time on this. I will first give a very brief introduction on the pseudogap phase in cuprate materials, then give you the physical picture. The picture is basically that we are studying a fluctuating magnet as a source of the pseudogap behavior. The question is how to do this as a theorist, also to come up with actual calculations. And this is what the rest is all about. Sorry, I have to get used to this. Computation of parameters. Most important parameter here will be the spin stiffness, calculated in some ordered reference state, but the final state will be one with ordered magnetism and then fluctuations on top, which destroy the long-range order. I will present a little digression, since we do a lot on spiral magnetism, which is important in many respects. It gives some features which Néel as a background state does not give, you will see. And so give some background here how to compute the stiffnesses there. And then finally, the low energy theory for the spin orientation fluctuations, which will be a nonlinear sigma model, how it will be solved. That part is fairly standard. Then electron spectral function, and finally some short outlook. All right. It's a bit counterintuitive here. The backward is down here. Okay. So introduction. Yeah, I guess you have all seen the structure of cuprates somewhere. Phase diagram as a function of hole doping, the hole doping in the planes, and the rest is just chemical stuff, so bringing in carriers and ultimately in the planes, and connecting, of course, things in the third dimension. Okay, as a function of hole doping here, that's for the hole doped class, which are the most important ones, and temperature, superconductivity, established as D wave. Then in the undoped parent compounds here, you have these, well, there's this antiferrometric order. Then here's the pseudogap regime, which is the focus of today's talk. Then there is more stuff, charge order, and also strange metal here, above optimal doping. So very complicated phase diagram. After all, the focus here is on the pseudogap regime. Okay, just a few features of that pseudogap taken from experiment. One is these Fermi arcs, sort of the big Fermi surface of the non-interacting system, or what you have at large doping, is truncated, sort of spectral weight appears from low energy at these antnodal points, and you get what looks like arcs. Furthermore, that's more recent actually, in high field experiments where you suppress the superconductivity, people have seen as a function of temperature. So here's again the phase diagram, and I go in this direction now, sort of reducing doping, and what you see is that the Hall number, which is loosely speaking a measure of the charge carrier density, drops dramatically as you enter into the pseudogap regime upon reducing the hole doping. So there's a dramatic drop, roughly from 1 plus P, P is the hole doping, which is the volume of the big Fermi surface, to P, which is the volume of something smaller. Okay, in our theory it will be just hole pockets. All right, and there is also nematicity observed in parts of the pseudogap regime. Nematicity means that even though the structure of the system is almost tetragonal or even perfectly tetragonal, in certain regions in the pseudogap regime, you see a breaking of this C4 orientation symmetry down to just something twofold. So you have just two directions where you have these intensities here. This the neutron magnetic structure factor, and established already almost 20 years ago by now. And finally, that was actually one of the first inside the pseudogap regime. You see a spin gap. So as you lower temperature, sort of you see a spin gap. So there are no low energy spin excitations in the pseudogap regime. So that's the sort of things one would like to explain. Of course, there have been many proposals in this field. Almost everything has been already proposed. Yesterday I learned about a new proposal I did not know about, based on magnetic monopoles by these gentlemen here. The talk was given by Carlo Rugenberger, which is a very beautiful thing, and I would like to learn more about this. More standard things here, very early, Tremblay and Wilk try to invoke already at an early stage spin fluctuations to get some pseudogap features. They got a loss of suppression of spectral rate at the antinode, but many other things they didn't get, and they require to get this large spin correlation length. And in reality, in these systems, the spin correlation length in the pseudogap phase is actually not so terribly long usually. There are cluster DMFT. DMFT means dynamical Wheel-field theory calculations, which is just hardcore numerics applied to 2D Hubbard model or other models for CUPRATES, mostly Hubbard. And there actually many features of the pseudogap are seen to the extent that the relatively modest momentum resolution in these types of calculations sort of can be seen. And so far as I understand, there was no nematicity seen so far. But these calculations, to me at least, show that in the most popular models in this field, like 2D Hubbard, that there is pseudogap, first of all, and second, in what has been called fluctuation diagnostics in this paper by Gunnarsson et al., people really figured out that it's the spin fluctuations that do the pseudogap in a Hubbard model. You can debate whether the Hubbard model is enough, but in the Hubbard model, this is seen in numerics. And basically, we would like to provide a deeper and more intuitive understanding of what is going on here, because this is just numerics. We would like to get the nematicity, and we would like to get better momentum resolution. Yeah, and then there are all sorts of other things, REB state, singlet formation, that also leads to some gauge theory, quite different from ours, not to be confused, Greenfield-Cooper pairs and so on. So what I would like to propose here is an SU2 gauge theory, which comes with some topological order, not the classical long-range order. It goes very much along the lines of what has been proposed a few years ago by the Suchdev group. We extend this in two respects. First of all, we actually compute things sort of ab initio from the Hubbard model, especially the spin stiffness, and we extend the things such that we get this nematicity. And this goes by extending things from Néel as the sort of ordered state below the thing to a spiral state. These are the main new features. All right, so I guess we all have seen this hundreds of times, part of the Hubbard model. So let's first present the physical picture. To do this, I discussed right away the spiral case, but sort of the usual standard Néel antifermi is just a special case of this, where this wave vector here is going to pi. And here's a picture of the spiral state. It looks like this. So it's a slightly tilted Néel, so to speak. Nice thing about spiral is that even though this can be terribly incommensurate, it still leads just to a splitting in two bands and not more. This is quite different from any other incommensurate state where you have plenty of bands. So here you have just two, and this is actually prerequisite prerequisite, you know what I mean, to get then just nice arcs and not dozens of fragments of some Fermi surface thing. Here are some dynamical mean field results for such a spiral state in the Hubbard model at strong coupling, namely the quasi-particle Fermi surfaces at various dopings, lower doping, higher doping. And what can be barely seen here, unfortunately, for some reason, it was nice on my screen, is the single particle spectral function in some sort of color plot. And here you would see something like half pockets, while here you have a big Fermi surface. And these, so what looks very asymmetric here on the level of Bogoliubov type quasi-particles gets more symmetric if it comes to the single particle spectral function, because there are weight factors and there is a superposition of up and down, and so this looks more reasonable than that. But this is just what you get from the spiral state. Okay, in the case of Néel, by the way, you would have just here 4 small hole pockets, but in the spiral this gets asymmetric and you may have just these 2. Okay, what we computed also in some precursor work here was this charge carrier drop, or more specifically this Hall number. And you see as a function of doping, these plots are different temperatures. That's here the ground state and higher temperatures, that you get at least qualitatively this drop as observed in the experiments. And this simply because you lose, of course, charge carriers by truncating this full thing and getting just to these pockets, which can be whole, and also these blue one actually are E-pockets, so filled with electrons. Okay. Yeah, but this is just the mean field picture, dynamical mean field here. So we have long-range order, and this is not what we have. So we would like to get rid of, keep some of these features, but get rid of the long-range order. That's the thing. And we would like to get a spin gap in particular. So the cartoon picture is we start with this mean field state and then put some fluctuations of the spin orientation on top, because these are the fluctuations that ultimately, according to Mermin-Wagner, destroy the long-range order at finite temperature in a 2-dimensional system, and possibly even the ground state. That depends on the strength of these fluctuations. So what we would like to do, we would like to have a theory where we can rotate our spin by some rotation matrix and put in fluctuations like this. Now, technically, we do this as follows, and this goes back actually to early work by Schulz, was picked up later by these people here, and then Sachdev and Scheurer picked it up again to link this to a theory, or to make a theory of the pseudogap in CUPRATES out of this. Boresia and Dupuy focused just on half filling and showed how it works there. There's things that are more simple, but in principle, we just extend this to spiral and away from half filling. So yeah, so we have this decomposition, the C operators, that's on the level of functional integral. C operator, these are the real electrons, and it's written as a product of some rotation, SU2 rotation, and what is called chargons. These are also fermions. They carry a pseudospin index, and this rotation allows me to treat these fluctuations of the spin, which I do not have in the mean field theory. So that's described in here. So of course, we introduced here more degrees of freedom than we have in the original theory. So there is an SU2 gauge freedom here. You can multiply this R with some SU2 matrix V, and also the size and everything remains the same. So there's a gauge, SU2 gauge redundancy here. But this framework allows us to do the following. If we find a state where these chargons order, but the fluctuations of these rotations sort of lead to expectation value 0, then we come up with something which does not have long-range order, but we keep stuff that comes from this chargon order. All right, now plugging this decomposition of the electron operator into these chargons and spinons into the Hubbard model, we get a Hubbard model coupled to a SU2 gauge field, and this gauge field comes from gradients of this rotation. So it looks just like Hubbard, but there is this coupling to the gauge field. Now, to compute the low energy theory, which is a nonlinear sigma model here for these spin orientation fluctuations, you can integrate out the chargon fields somehow at this point. Later I will tell you how we do it. And then expand in these gauge fields, which are these gradients of the rotation. And then you come up with a nonlinear sigma model, and the parameters are the spin stiffnesses, which have to be computed somehow. In the theory by Suchdev, this was okay for Néel. This is here for spiral more general, and stiffness was just fixed by experiment. So how do we compute parameters? How much time do I still have to speak? Just I think I'm a bit slow. 10. Okay, that's great. Okay. So here to compute now parameters, there are two things to compute. First, the chargon order, so to speak, the magnetic order, which order, spiral, Néel, what is the size of the magnetism, and then the spin stiffnesses we need for this nonlinear sigma model thing. So let's start with the chargon part. Here actually I restrict myself for the moment to Hubbard model with a moderate U. The reason at the moment is we have not yet the technicality to compute stiffnesses at strong coupling, but this is a coming up project. So we could compute, I showed you previously results for the magnetism in DMFT, but now I go a bit more modest to moderate U and compute things there in a certain framework. The nice thing is that all these pseudogap features you get already at moderate U. You don't need strong coupling for that. Okay, so what we do is here some sort of renormalized mean field theory, which is a combination of what is called functional renormalization group. I've worked a lot on in the last 2 decades. With mean field theory, that's a way at moderate coupling, quite nice way to compute order parameters, but such that fluctuations coming from high energy are built in. So in particular, in this gap equation for the magnetic order, sort of delta B, where it's not a superconducting gap here, I'm not talking about superconductivity in this talk at all. The magnetic gap is computed by a sort of gap equation for spiral or Néel, and this is the coupling going in, and this coupling by these fluctuations treated by the RG is much smaller than the bare Hubbard coupling, and so we get reasonable values for this regime where something interesting happens. If you did just pure Hartree-Fock, everything would be terribly overestimated. Okay, that's maybe all one should know about this. And we of course optimized for the gap, but also for the wave vector of our spiral state. And so sometimes it will be Néel, sometimes it will be spiral. And this you see here. This is the chargon phase diagram for Hubbard model, 2D Hubbard. The coupling U is 4 here. It's as a function of density. And you see on the hole doped side, it's quite different from the electron doped side. Here's half filling. And this asymmetry comes because we have a T prime. Now, a next nearest neighbor hopping, and all the cuprates have such a T prime. It can be smaller, it can be bigger, but it's always there. And that's crucial to get this particle hole asymmetry. And you see already on this level, this asymmetry. Here's temperature, density, as I said. So here's Néel, and here is spiral. That's the only states we allow. If you extended this and allowed also for stripes and all those sort of things at low temperatures, here you would also get stripe states, as we have seen. But here we are more interested in a generic finite temperature thing, say up here, where we see the pseudogap, and not going into these very delicate balance of energy in the ground state. And then, of course, you would also have pairing to consider. So let's stay at intermediate temperatures, and there we have Néel or spiral. Okay, the spiral will ultimately give rise also to the nematic, because the spiral breaks the orientation symmetry. But here on this level, we break not only orientation symmetry, we also break translation, violated by Wagner, so spin SU2 is broken. But this will be cured by this fluctuation part I'm coming to now. Okay, to do the nonlinear sigma model, that is the low energy theory for these spin orientation fluctuation, we need spin stiffnesses, which are the parameters in this nonlinear sigma model. And these are computed or come out from this theory by computing the response to an SU2 gauge field, as you have seen in this decomposition. And and this is a bit lengthy story to really carry it out. but we do this corresponding to the mean field nature of this calculation so far. The stiffness is computed on some sort of RPA, and you see the usual paramagnetic, the diamagnetic term, and what you don't have in a superconductor, but you may have here, because the symmetries is different, also some RPA type corrections. All right, so yeah, very briefly digression, sort of this response to the SU2 gauge field is actually linked to the stiffnesses as defined as expansion parameters of the spin susceptibility in frequency and momentum around the Goldstone points. And this is something that has been done by Pietro Bonetti, just single authored, already published. The link comes via, not surprisingly, via wall identities coming from the SU2 symmetry. And here just flash the formula. So there are two ways actually to get these stiffnesses. One is computing the gauge field response, like here, and the other is taking the spin susceptibility at the Goldstone point and compute the leading frequency and leading momentum dependence of the Goldstone poles. Okay, but I leave it for time reasons that short. Now, okay, we have been, I think, the first to actually compute spin stiffnesses in such a spiral state, and there's quite some behavior, and there are also in the spiral many spin stiffnesses because you have the in-plane Goldstone mode, you have two out-of-plane Goldstone modes, and then you have the spatial part and the temporal part. The temporal part is the prefect of the omega squared, sort of the dynamic part of the susceptibility. And you see here can you see this? And so this is the out-of-plane stiffness, this is in-plane stiffness as a function of doping. Again, here's hole dope, here's electron dope. And what is really a striking feature is that here this vertical line is half filling. And as you hole dope, there is a dramatic drop of these spin stiffnesses from the half-filled result due to the hole pockets. So even if tiny, they give a big contribution, and this means that as soon as you have some hole doping, the tendency, the fluctuations get much bigger, because small stiffness in the sigma model means, of course, that fluctuations are getting more important. All right, so, and you also see a particle-hole asymmetry. The fluctuations will be stronger on the hole dope side compared to the electron dope side. All right, let's skip this. We also analyze the damping of the Goldstone modes, but let me skip it. And back to the low energy theory. Now we have the parameters, and we have to solve it. Okay, we solve the sigma model in a fairly standard model. This type of sigma model came up already in the 90s in the context of frustrated antiferromagnets. There's a work by Azaria et al., but there are many others. And we do just the leading order 1/n expansion, extending the symmetry group to large n, and then 1/n expansion. That part is fairly standard, and you get some equations for the order and for the spin gap. And what you get here, and that's nice, is already the leading order in 1/n gives you the Mermin-Wagner theorem, so you don't get long-range order at finite temperature. But you get a spin gap, no long-range order, while in the ground state you have the possibility that you still get some condensation. This is here the condensation in this framework, which corresponds to some sort of long-range order, reduced in general, of course. And yeah, whether at t equals 0 you get long-range order or not, that depends on the stiffnesses, and there is a critical stiffness below which you don't get, you get a quantum disordered state, and above you get an ordered state. Now in our case, in the ground state is ordered, but at finite temperature, of course, we have the non-ordered thing. Now, finally, we would like to get back also to the electron spectral function. And if you remember that I decomposed the physical electrons in this funny way, in 2 degrees of freedom, to compute now the electron green functions, to compute the spectral function, we need to take actually expectation value of C and C dagger with these things. So it's a 4-point function in a sense. The simplest thing to do is to just decouple this. This is also done by Suchdev and company. And we have so a spinon green function with the spinon velocities and the spin gap. And we have the chargon part, which has this 2x2 structure due to the spiral on the L order. Okay, and now at finite temperature, the spinon part makes sure that we don't have long-range order, but nevertheless, in the spectral function, we still see features that come from these pockets. And if you look here at this low doping, 5%, these are the Vogel-Neuhoff mean field quarter particle Fermi surface, and this is what we get on the level of spectral function as computed now from this little scheme. And we see that really looks like the experimental arcs. But it's just in a sense inner part of pockets, and you don't see the back bending because the spinon fluctuations smear the whole thing, but also in experiments things are much smeared, and so this looks really very much like the experiment. All right, yeah, so at higher doping, of course, you reconstruct the big Fermi surface. All right, yeah, that's basically all. And let me summarize. So we have this theory of a fluctuating magnet, and we get many features that are observed in pseudogaps, and it's a relatively simple physical picture, and it can be linked to microscopics. Things can be worked out for the Hubbard model. So we have this finite temperature pseudogap regime. In particular, we have this transition into a nematic state, which comes from the spiral inside the pseudogap here. We get the Fermi arcs, and since we have small charge on Fermi surface, also this charge carrier drop will survive. There, the spinon fluctuations just cancel out in the charge transport. Yeah, I didn't talk about this outlook. Of course, one would like to maybe put in now the superconductivity, analyze maybe also stripes, and more importantly, maybe we would also like to go to strong coupling. We know already how to do it via DFT, but we still need to develop some technicalities for that. All right, so thank you very much for your attention.
You essentially described a theory of matter in the pseudo state, in the pseudogap, right? The electrons, separate, spin.
Yeah.
Suppose now you couple the charge part to a real electromagnetic field. And what is the effective action that you get when you integrate out this SU2 model? Did you compute that?
No. I'm afraid I have to think about this. Actually, so far we haven't done any superconductivity.
No, I'm not saying that the superconductor comes out, but I would be interested to see what comes out. What is the effective action for the gauge, the real gauge?
Of what you presented in your talk also, right? Very much just sort of in mind.
I wonder if there is a
so the state is still in metal. So if I argue from that side, because we have these Fermi surfaces, the charge and the electromagnetic field couples to the charge. The charge is not affected by the spinon fluctuations, so it's very much not like a conventional metal. Now remember that you said something T-squared behavior at low. That it would get because the charge part has it's
the T-squared. You have to have a metal which does not scatter. If you have scattering, you don't get T-square.
So you mean you have you don't have scatter by
if otherwise in a metal you get T to the fifths.
With the phonons.
Whatever.
Sure.
You have to have a
T-squared
Fermi liquid.
T-squared would come from the electron-electron interaction, right?
Yes.
That's sure. Yeah. Of course, I would need some residual electron-electron interaction, which will also be able to.
Yeah, but you should.
Otherwise, I would.
But you should show that what you get does not scatter to any phonons or to any other things.
Actually, we don't have phonons.
You don't have phonons.
So my the system has but my lifespan goal is to do things for the Hubbard model, and then it's the next generation. Sure. So of course, CUPRATEs is very rich thing for Hubbard itself.
About the finite Q and
the finite
Q
Q dependent. So for the spiral, you have finite Q. Is there any indication from neutron, for example, or anything that connects this Q with experiment and pneumatic state? I take that it's
connecting to pneumatics. I don't know, but it's well known experimentally that the spin correlations, as you told, do not remain at pi, but you have something incommensurate, and the incommensurability, that is the deviation from the Néel pi, that increases with doping typically, and this is what we also get.
And how you would like to connect it with pneumaticity? What is the mechanism?
Yeah, so our mechanism for pneumaticity is that if you get an ordered state where the wave vector of the order is not pi, but some spiral where the Q vector is different from pi, and the form of this wave vector is, maybe it takes too long. So the Q we get has a form pi minus some delta, comma pi. So it has a preferred direction. Of course, we could also go the other direction. That's just a matter of how we break the symmetry. But that is already on the level of the mean field state some preferred direction. And now on top we put these spin fluctuations, which destroy this long-range order, or the spontaneous breaking of the SU2 symmetry. But you're left with this orientation symmetry breaking, and that's the pneumaticity. Thanks.
Yes, I have a question. It is known that in the pseudogap phase there is a diamagnetic response below T star and above Tc. Does your theory reproduce something like that?
Not yet. Sort of. We have some calculations on a renormalized mean field level without spinons yet, where we compute also the pairing temperature in such an RG type mean framework, the pairing scale, and of course the Soulis temperature. And so on the scales as such, we first get a T star is here, and then at a somewhat lower scale, inside this pseudogap thing, we get a pairing thing, where the pair gap from the Cooper pair forms, and still lower across the Soulis temperature, where we get actually the transition. I don't have a picture here, but this is what we get in our calculation. Then I know that in experiment people see different things sometimes, but okay, not everybody agrees.
But just your get antiferromagnet does not reproduce, of course, the diagrammatic response.
Yeah, we didn't look at the diagrammatic response, but as soon as you have the conductivity, of course, will be a perfect diamagnet, and above that scale, there will be some fluctuation contributions, which this one could merge out and should come out at least below the scale which we find for the formation of Cooper pairs at a certain point, but very little.
And one more short question: do you have correlation lengths for magnetic structure? Because you use mean field.
Yeah.
How about correlation lengths, magnetic correlation lengths?
So what we can compute is if you go in the symmetry broken state, then actually the spin correlation inside the symmetry broken space state is a 4x4 thing coupled to charge. There's charge, then there's the longitudinal in the direction of the spin order, and then two transverse directions. The two last one have to do with the Goldstone modes, and the longitudinal one, that decays exponentially, or there's a gap, and from that you can get something you might call the coherence links or so, and that is short. Even at moderate coupling, it's just a few lattice sites.
Thank you.
Thank you. Okay, thank you.